In this video, we're going to apply our material balance framework in order to analyze a reactive process that involves an equilibrium reaction. And so what we have going on is a reactor in which carbon monoxide and hydrogen gas form methanol. All right? And for the stoichiometry of this reaction, it's 1 mole of carbon monoxide and 2 moles of hydrogen gas form methanol. And since it's an equilibrium reaction, the reaction can also occur in the reverse direction as well. Now, the mole fractions of each of these species are related by an equilibrium constant, and that relationship is defined here, where each of the variables is defined in the text. Now, the problem statement tells us some information about the equilibrium constant. It tells us the value of the equilibrium constant at two different temperatures, 373 and 573 K. It also tells us that a semi-log plot of the equilibrium constant, in which the natural log of Ke versus 1 over T is approximately linear in this temperature range. All right? And so using this information, the problem statement asks us to solve for a couple of things. All right? And so in this video, we're going to solve parts A, B, and C of this problem. Okay? So to start this problem, I'm just going to write down a few pieces of pertinent information. I wrote down the reaction here, and I'm going to call carbon monoxide A, hydrogen gas B, and methanol C. And I'm doing that just for brevity, just to make writing down all the chemicals and species much easier. Okay? So I wrote down the reaction, and I also wrote down the equilibrium constant equation that we're given. I want to say that this relationship, according to the text, is an empirical relationship. All right? And so this is what the relationship that they determine based on doing experiments. I also wrote down the equilibrium value, or equilibrium constant values at the two different temperatures. And I wrote down that this equilibrium constant obeys a linear relationship with the reciprocal of temperature. Okay? And so let's start approaching this problem step by step. So for part A, the problem asks us to figure out what is the value of the equilibrium constant at a temperature of 450 degrees Kelvin. Okay? And so to approach this problem, to answer this question, I'm actually going to invoke this piece of information, where it tells us that the natural log of the equilibrium constant is linear with respect to 1 over T. Okay? And so what that means is that if we calculate the slope of Ke, the natural log of Ke over 1 over T, right, this slope value is going to be equal to a constant. Essentially, if we took the difference between two values of the natural log of the equilibrium constant at two different temperatures, and then we also put that over the difference of the reciprocal temperatures, that ratio is going to give us a constant. Okay? And so that's what this linear piece of information tells us. And so using this piece of information, we could apply it in this way. And so when I wrote here, I wrote the delta, right, the natural log of Ke. And so we're given two values of Ke at these two different temperatures. So what I'm going to do is I'm going to write out this relationship. All right? And so we have the equilibrium constant at 573 K minus the equilibrium constant at 373 K. And then I'm going to divide that by 1 over 573 K minus 1 over 373 K. Right? And so this is just this relationship, but written out using values we know. All right? And so the key here, the problem statement wants us to figure out what Ke at 450 K is, right? And in order to figure out, we need to harness the linear relationship. We know that the ratio here is a constant, right? And so what we could do is we could equate this left-hand side of the equation to a similar term on the right-hand side. But instead of writing 573K, what I'm going to do is I'm going to write the equilibrium constant for 450 Kelvin. All right. And then on here, I'm going to write the 373K one. And in the denominator, I'll write this out. Okay. All right. And so on the left-hand side, I basically wrote delta K, natural log Ke over delta 1 over T. And on the right-hand side, I wrote that as well. All right. The only difference is on the left-hand side, I have 573K here, and on the right-hand side, I have 450K. All right. And the useful thing about this relationship is that I know the values for this, and I know these temperature values. All right. And I know the equilibrium constant value here and these temperature values. And really the only unknown I have is this. Okay? And since I have one equation and one unknown, that means I could rearrange this and solve for that unknown. So I'm going to rearrange this equation. All right? And by doing a little algebra, I could determine that the natural log of the equilibrium constant at 450K is equal to minus 2.9. And if I take the exponential of both sides, I get that the equilibrium constant at 450K is just equal to 0.548 and then 1 over atmosphere squared. Alright. Now the units I'm writing here, it's not quite apparent where that came from, but basically if you look back at the equilibrium constant equation that we're given, which is an empirical one, you see that we have a pressure term in the bottom, 1 over P squared. Right? All these mole fractions here are going to be unitless, and so really the only units we have for this equilibrium constant come from that pressure term. Alright, so I'll just write here. First I'll square this since this is our answer. And I'll write here based on empirical equation. Okay? Alright, so we figured out what the equilibrium constant at 450K is just by exploiting this sort of linear relationship. Alright? Now you may have seen this process before, and what we did here is actually a process that you're going to use quite a bit in this course. And so the act of, equating essentially the slopes for different values to each other, what we call this is interpolation. Alright? And whenever you're dealing with tables of data and you're trying to find the value of some sort of parameter, but the table doesn't give you the specific temperatures that you want, a lot of times you're just going to have to interpolate the value in order to figure out what that parameter is. So that was for part A of the problem. Let's now move on to part B. For part B of this problem, essentially what we want to do is we want to determine a mathematical relationship that allows us to describe the moles of species A, species B, and species C, and also their mole fractions. And for this mathematical relationship, it wants us to describe it in terms of the initial amount of moles of each species and also the extent of reaction. Okay? Alright, and so the extent of reaction we reviewed in a previous video But basically, the way it's defined is it's going to be the number of moles of a species I minus its initial number of moles, so the little knot there, and then it's going to be divided by its stoichiometric constant. Alright? And I just want to remind you what the stoichiometric constant is. It's basically if we go back to the equation, it's basically the stoichiometry that we have in front of each species in our reaction. But depending on whether we're dealing with a reactant or a product, the sign of the stoichiometric constant is going to be different. Okay? And so if we're dealing with reactants, the stoichiometric constant is going to be negative. And if we're dealing with products, stoichiometric constant is going to be positive. All right. Another useful thing about the extent of reaction is that it's the same for all species in the reaction. In reaction. All right? And so, to illustrate that, for the process that we're dealing with here, we have 3 different species. All right? So, if I write out the extent of reaction in terms of species A, what we get is this. Right? Where we have the number of moles, that's sum at the final time point, minus the initial number of moles, and then divided by its stoichiometric constant. And here you see we have a -1, because if we go back to the reaction, we see that this 1 mole of carbon monoxide is consumed in this reaction. And because it's a reactant, there's a negative sign there. Okay? And so that's the extent of reaction in terms of species A. But we could also write it in terms of species B. Right? And on the bottom here we have a -2, right? Because 2 moles of hydrogen gas are consumed in the reaction. And we could also write it in terms of species C. And right here we have a +1 on the bottom because 1 mole of the methanol is produced in this reaction. Okay? And so the extent of reaction is equal to all these things. Right? You can see that I wrote the equal sign here. Now, what we could do is, in the problem statement, we're essentially told we know what the initial amounts of each of the species are, but we don't know the final amounts. Right? And so what we could do is we could rewrite these relationships for the moles of species A or species B or species C in terms of the extent of reaction. Right? So essentially what we're going to do is we're going to move all this stuff and multiply or use algebra and move it to the left-hand side. All right? So for example, for species A, the moles of A is going to be equal now to this. All right? And if I do the same for species B, okay? And if I do the same for species C, it's this. Alright? So we have the moles of each of the species in terms of their initial amount of moles and also the extent of reaction. One other thing I could do is I could also add all these things up. Add the moles of each species up. And that will give me the total number of moles. So NT is the total number of moles in the system. And that's just equal to Na plus Nb plus Nc. And if I add all these up together, I get this equation. So Na naught plus Np naught plus Nc naught. And then if we add up all the extent of reaction terms, I'm left with minus 2 Kc. Right? A couple things I'll point out here. These initial amounts of moles, these are all constants, and I'm just going to recast it or redefine the sum as just a new variable called nt naught. Right? So really what we have is nt naught minus 2 times Kc. Right? Now one interesting thing, if you take a look at this, right, this sum here, we are calculating the total number of moles. And the way it's described, the total number of moles in the system is equal to the initial amount of moles in the system minus 2 times Kc. Right? And if you remember in the previous video, when I described the extent of reaction, I basically described it as a way to quantify how many times the reaction occurs. Right? And so the more moles you react, or the longer your reaction runs, your extent of reaction increases. And so the extent of reaction will start at 0, right? And then it will increasingly become more positive. And so if it becomes more positive, that means this term becomes larger, right? And since we're subtracting from mt naught, what that means is that over the course of the reaction in our system in this problem, we're actually decreasing the number of moles. Right? And so this reaction proceeds, NT decreases. And that makes intuitive sense, because if we go back to our reaction here, right, we have 1 mole of CO and 2 moles of hydrogen gas, so 3 moles total on the left-hand side, only becomes 1 mole of methanol. All right? And so here I wanted to point this out because this highlights, or this is an example of a case where the number of moles in your system is not conserved. All right? Okay, but in any case, the main useful thing for this problem about calculating the N total, or NT, is that we could use this for when we need to calculate for the mole fractions of each of the species. Right, because the mole fraction is just the number of moles of species A divided by the total number of moles. Okay? And so we know what Na is from this equation. Now we know what Nt is. And so we just need to plug those in. And we could do the same thing for the other species. Okay, so we figured out the mole fractions, and we also figured out the total number of moles for each species. So I'm just going to box them in here. All right. Okay, now for the most part we have most of part B done, but part B also asks us for one more thing. It wants us to figure out what the extent of reaction would be at equilibrium. Okay? All right, and so the way to figure that out is we could actually go back to our equilibrium constant relationship that we're given, that empirical relationship, which is that Ke is equal to Yc over Ya Yb squared times 1 over P squared. All right, so that was given in the problem statement. But from our work on the previous page, we now have mathematical relationships for Ya, Yb, and Yc in terms of the extent of reaction. So let's just plug those in. So Nc naught plus 1 times Kc E here. And the reason I'm writing this sub E is because now we're calculating the extent of reaction specifically at equilibrium. Right? Before, we kind of just had it, we were just saying the extent of reaction is equal to this. Right? But at equilibrium, specifically this relationship is true. Alright, so I want to emphasize it's only at equilibrium when you could apply this relationship. Right? Not at the beginning of the reaction when you just start. It's only when you achieve that equilibrium condition. Alright, in any case, let's fill in. Well, actually, what I'm writing here is after you plug in for your YA, YB, and YC. Okay? So and B minus 2 times squared, and there's a 1 over P squared here. Okay? And so this is the relationship that relates your extent of reaction now to your equilibrium constant. Alright? I want to emphasize that this C sub E is the extent of reaction only. Alright? With an underline there. So we did all this work deriving relationships that connected the equilibrium constant that we measured empirically to a mathematical formula. And the reason for that is because now in part C, we're going to be applying this sort of relationship to help us solve a material balance problem. Okay? And so in part C, it's telling us that, suppose that we start our process with equal molar amounts of carbon monoxide and H2 gas and no methanol, all right? And that our reaction proceeds to equilibrium at this temperature and this pressure. And the problem wants us to solve for the molar composition of the product, the mole fractions, and also the fractional conversion of carbon monoxide. Okay? And so, based on the information in this problem and the information that we had in parts A and B, what I want you to do now is I want you to pause the video and I want you to draw out the process flow diagram. So from the problem statement, we could draw a process flow diagram that looks like this. All right? And so, for our basis, it told us we had equal molar amounts of the carbon monoxide and the hydrogen gas and no methanol. Right? It didn't really tell us an amount, but in the end, we only care about mole fractions and fractional conversion. And so what I could do here is I could assume that we have a basis of just 1 mole of the carbon monoxide. Okay, and so in this case, if you're given mole fractions and things like that, you could usually just assume a basis. All right, and so that's what I'm doing in this case. I'm assuming a basis of 1 mole. All right, in any case, so we have 1 mole of the methanol species A and 1 mole of species B going into an equilibrium reactor. And out of that reactor, we have some amount of stuff, reactants and products combined. And what we're concerned with is the mole fractions of these things. Okay? All right? And we also want the fractional conversion, which I call F sub A as well. And so at this point, we need to determine if we actually have enough information in order to solve our material balance. So to do that, I'm going to do a degree of freedom analysis. But because we're dealing with an equilibrium reaction, I'm actually, rather than doing a molecular balance or even an atomic balance, I'm going to do an extent of reaction sort of degree of freedom analysis. And so for this sort of analysis, what I need to count is our number of unknowns, the number of reactions we have going on in the system, the number of independent species, and any sort of other equation that we could use. Okay? So at this point, you should pause the video and you should count up, each of these categories to see if we have enough information to solve for all the variables. Okay, so let's count up these categories. Now for our number of unknowns, really we have the total number of moles in our product stream, or coming out at the end, the mole fraction of A, and the mole fraction of B. For the mole fraction of C, we know, since we're dealing with 3 components, that it's just going to be related to the mole fractions of A and B, right? And so we're not really going to count this one as a variable, right? Because if we know these two, then we could figure out that one, right? So really, the number of unknowns we have are 3. Right? The number of reactions we have going on in this system is just 1. Right? We just have one equilibrium reaction going on. I want to emphasize is that even though the reaction can go backwards, we're not counting that part as a separate reaction. Right? So we just have one equilibrium reaction. As far as the number of independent species, we have 3. Right? We have the carbon monoxide, hydrogen gas, and methanol. And as far as other pieces of information that we could use, what we could do is we could actually use that equilibrium relationship that we're given in the problem statement. Right? That empirical equation. Right? And so for our degree of freedom analysis, what it's going to be equal to is the number of unknowns plus the number of reactions minus the number of independent species minus anything else. And in the end, we get 0. And so this tells us that we could solve for all of our unknowns. All right? So I'm going to go to the next page here. And so this problem, it's asking us to figure out the molar compositions of all of the species at the end. All right? And so to figure these things out, Y2A, Y2B, and Y2C, one important piece of information we need to figure out, we're told this reaction goes to equilibrium, so we need to figure out essentially what the extent of reaction is at those equilibrium conditions. So we need to figure out E at 423 K and 2 ATM. Right? So just to emphasize, we want these things. And part B, we figured out how these things are related to the extent of reaction. All right? And so we need to figure out the extent of reaction at equilibrium, which in part B we were also told comes from here. All right? Here's the relationship we need to use. All right? And so, but first, in order to solve for CE, we need a value of our equilibrium constant, our K sub E. All right? And so, first I'll just kind of write down what I was trying to explain. We could use the K sub E equation we derived in part B to get this, right? But in order to solve for CE, we actually need to know what our equilibrium constant is. Ke is at 423 Kelvin. Okay. All right. So we need K sub E at 423 Kelvin and 2 ATM. So how are we going to do that? What I want you to do now is I want you to pause the video and kind of think about what we're going to do in order to get that. To get K sub E at a temperature of 423 K and a pressure of 2 ATM, what we're going to do is we're going to repeat the same strategy that we used in part A. All right? Whoa, I can slide. Which is, we could just interpolate a value of K sub E using this relationship. Okay? And so instead of plugging in 450 here, we'll just plug in 423. All right? And so I'll leave it to you to work out the interpolation. But I'm just going, for brevity, I'm just going to write out what the answer ends up being. Okay? So for 23K, we get a equilibrium constant of 0.278 1 over atmosphere squared. Okay? And so work that out at home and make sure that you get that same number. Now that we have this value, we can now plug it in to this equation. Or specifically, we could plug it in there. So let's do that. So we could plug in the equilibrium constant that we just calculated, and we'll now set it equal to that equation we derived. Okay. T naught 2 times squared V minus 2. Okay. And then that's over 1 over 2 ATM squared. Alright, now in this equation, we have a bunch of values for the, oh, there should be a knot there. For the terms of the moles, initial number of moles, we're actually given that in the problem statement, right? Or we assumed a basis. 1 mole, and then 0 moles for the methanol. So we could actually plug those in. So this is 0. This is 1. This is also 1. And if we add those all up, we get 2. 2 mole, 1 mole, 1 mole. Alright, and so really the only unknown we have in our relationship right now is the extent of reaction at equilibrium. So if we just rearrange the equation and we simplify it a bit, what we actually end up getting is a quadratic relationship. .317 equals 0. Okay? And since we have a quadratic relationship, we just use the quadratic equation to solve for Kc sub E. And from the quadratic equation, we should get 2 roots. Okay? Alright, so we have 2 answers, but which one should we use? We could figure this out by actually just kind of seeing, plugging these numbers back in to our equation. Alright? And so if we plugged in, 0.156 into here, you would get 1 minus about 0.32, and so that would be a positive number. Okay? So this root checks out. But if we plugged in the 0.844 into here, we would get 1 minus 2 times 0.844, right? And that would give us actually a negative number. Right? And essentially, it would be telling us that we have negative number of moles of species B at equilibrium, right? Which does not make sense. And so, what we could do is we could actually just ignore this answer because it's unphysical, right? Mathematically, that's a solution to this equation, but in real life, you can't have negative moles, right? So we're just not going to bother with this one. Alright, so we're just going to only worry about the 0.156 value for Kc sub E. Alright. And then what we're going to do is we're going to plug in this value into our equations that we derived here. Alright, and so if we do that, what we get is values of this. Alright. So there are our mole fractions. Alright, and for the last part of the problem, we need to figure out the fractional conversion. And so fractional conversion, in terms of species A, is just a ratio between the number of moles of species A that reacted minus the moles of A that you actually fed into the process. In terms of things in our problem, the number of moles reacted is just going to be the difference between the initial number of moles of A minus the final number of moles of A. And the Na fed is just going to be Na naught. Okay? Alright? But we could also rewrite this in terms of just the extent of reaction and the stoichiometric constant. Right? Because this is actually going back to our definition of the extent of reaction. Right? So this is the number of moles of A that was fed. Or number of moles of A that reacted right there. So that's where this equation comes from. And we could plug in the values for A. Our new A is -1, and our basis is 1. And so in the end, actually, what we get is 0.156. Okay? And that's our fractional conversion of A.